just starting to talk about the 0.25 cutoff, I think.
Okay, so we talked about the Levine test and how we set up this adjusted data, and there's the example 4 revisited again here, where Levine's test is carried out. And I didn't give you the hand calculations for this example, only on the top of page 11. The final ANOVA table is presented there from Minitab. And you can see the Minitab command that I used to produce this analysis of variance table is right there. So anyway, when we look at the p-value here, we see that it's greater than 0.25. So our conclusion is the hypothesis of equal variances is accepted. All right. So then the last part of this handout is on the rest of this page here. And basically what's going to go on here is that we're going to assume the model where the variances are unequal. So if I page back to where we talked about that model, how far back was that again? On page 3, notice how the model has all the variances equal. Then down here, the error terms in the model equation have common variance. So all of our models through this handout have been assuming this equal variance business, and that's fine. That's what we were trying to do. And then when we get to page 9, finally, here's what I was looking for. It talks about the unequal variance model on page 9. And so here the factored levels have populations connected with them, which have potentially different variances, notice. Different means and different variances, normal distributions still being assumed. And so the sample variances are denoted by these S squares. So that led us into Levine's test for testing the hypothesis that the variances were in fact all equal. So we continue with this unequal variance model, and kind of ignore that hypothesis about the variances and turn to this. So what we want to do, as it says here, is to test the hypothesis about two means being equal, or equivalently their difference being 0. And the way this is done without assuming equal variances is to use this so-called Welch T statistic. And there it is. So you remember the distribution of the difference between two y bars. So what we have basically is the sample difference of means officially minus 0 from the null hypothesis. And then we divide by the square root of the variance. Now the variance should be sigma 1 squared over n1 plus sigma 2 squared over n2. That's the variance. So if we want the square root of the variance in the denominator, that's what we would need to properly standardize the statistic. But the problem, of course, is that we don't know what these sigma squares are, so we have to drop down to another thought, estimate them from the data. So notice how here you're seeing the S's, the sample variances, appearing in that formula in the denominator. Now, this quantity doesn't have a t-distribution exactly, but it has what we call an approximate t-distribution. And then we have to worry about what are the appropriate degrees of freedom. And this paper that was due to Welch and a few other people at about the same time, Setter's weight, for example, was another author. They figured out via some, well, approximate mathematics, I guess I would simply say, that we can estimate approximately appropriate degrees of freedom to use for the t-distribution. And so the estimated degrees of freedom for the Welch t-test, I call it DFW here, is this big, clunky, messy formula. And notice that it depends upon the s's. Here's SI squared over NI, SJ squared over NJ. That's added together and squared in the denominator. And then in the denominator, you have that same thing appearing there, it's squared. You have the other thing appearing there, and it's squared. And so basically, this is kind of a messy formula. And the methodology behind this approximation doesn't come up enough for us to worry about what are the details. So we'll skip that and say, well, they figured this out. This is the way we estimate appropriate degrees of freedom for a t-distribution. So if we run a Welch t-test, here's the t-test statistic. Notice it's different than the regular t-test statistic. The regular t-test statistic would have a denominator which would be square root s, let's call it p squared, times 1 over ni plus 1 over nj. And the SP that I've written here is labeled the pooled sample variance. So pooling together the two samples come up with a single estimate of a sigma squared. So that's the denominator for the regular t-test, or we call it the pooled t-test. And I should write that word here. For the pooled t-test, we use that denominator. And then for the Welch t-test, we have a different denominator here. The pooled t-test has degrees of freedom Ni plus Nj minus 2. So we have some other different degrees of freedom for the Welch t-test. It indicates here at the end of this paragraph that we could write down, and I didn't here, we could write down a confidence interval formula for mu I minus mu j as well. Now, just to finish up this page with the last part of it, because I'm only going to say it lightly, suppose instead of a simple difference, we're interested in a full contrast. Some of the coefficients being 0 again would make it a contrast. Then there would be the sample contrast called psi hat. Plug in the y bars for the mu's. And the distribution of this sample contrast came up in an earlier page, would be this one right here. So if we want to test a hypothesis that the contrast is 0, which is usually the typical value that we want to test about, the Welch t statistic would be this one. So notice it has the denominator wrong. There's supposed to be a square root here. Sorry. Because it should be the square root of the variance in the denominator. So sorry, the square root there is missing. Add that into your page. And so we have the square root of the variance, but in the variance, the sigma squares, which are unknown, are estimated from the sample variances, Sj squared. So then if we're going to use this as a kind of a Welch t statistic for testing about the contrast, we need to know what's the appropriate degrees of freedom. And then the last line on this page getting that shadow from.
Actually, if you could angle the lights on your overhead to the side a bit, and then point them in. Yeah.
Well, that's not doing much for me. Is that the best I can do? Apparently.
That's good.
Well, luckily you have the page in front of your eye so you can look at it there more clearly than perhaps here on the screen. But this last line here is the estimated degrees of freedom for this Welch t-test about a contrast. And it's kind of a messy formula, but nonetheless, there it is. So this bottom part of the page just extends the idea that was above with the Welch t-test for a pair into the case when we have a contrast that's of interest. Now, just to try this out, I thought I'd go back to one of the earlier examples in this handout and see what happens with the Welch t-test. Now, I went to page 5 for example 1 sitting there. So this is a simple example about the car mileages again. And the reason I went back and picked on this one, because when I looked at the sample variances, 1.4, 1.7, 3.2, there seems to be some difference in these variances here. And so I'd like to know, how about if I do a Welch procedure instead of what was done on this page? Okay, so let's try to compare, say, 2 with 3, or even 1 with 3. Let's try 1 with 3. So that's down here below. The middle case is the confidence interval. Let's see what we get when we do the Welch procedure instead. So we have to do some work. So let's compare 1 versus 3. And so the denominator in the Welch t-test, should be the square root of, and then it should be S1 squared, which would be 1.41 squared over N1, which is 5. And then the other variance is 3.16 squared over that sample size, which is again 5. And so this is my variance. So let me try to work that out. You're probably faster than I am if you use your own calculator, but you can double check my punching as well later on. 2.395 is good enough. So I need the square root of that. And I get 1.54.
Excuse me.
Yes.
Why did you divide by 5?
Excuse me.
We have 4 observations.
Thank you. There are 4 observations, not 5. So I did it wrong. Fix it up.
It says in the problem 5 hunters, but there's actually only 4 observations.
Yeah, I wonder what happened here. I read the 5 from somewhere. How are these numbers adding up here? Let's see. Yeah, those 4 numbers add up to 148, so I guess it's only 4. Yeah. Sorry about that. I have to go back and start over again. So, divided by 4. So that becomes 2.993. And then when I take the square root of that, I get 1.73. Okay. Now the confidence interval formula that I'm trying to work with is going to be plus or minus t.025, and then some appropriate degrees of freedom, yet unspecified, times this 1.730. So what's the estimated degrees of freedom? So we have to go back to that formula. Let's see here. This is not a pleasant formula to use either, of course. There it is. So we're supposed to use degrees of freedom equal to S1 squared, and it's going to be a 4, right? Plus S3 squared over 4. And that's all to be squared divided by S1 squared over 4 squared divided by 3 plus S3 squared over 4. That's squared and divided by 3. So that's what I got to calculate out. Well, let's see. S1 squared is there, 1.41, and S3 squared is there, 3.16. So let's try it out and see what I get. Squared divided by 3. Now I have to do the bottom. So let's see. 2.1597. Okay, so finally let me divide these two numbers out. 15.93. I get 7.376. So there's kind of my hurried punching in the numbers, double check my work to see that hopefully you get the same thing, see how it works. And so my degrees of freedom should be rounded to what? Should we round up? Should we round down? I know of no official rule about this, so I just round. So I'll round that to 7.
Seven point three seven six.
Pardon?
Is it 7.376?
I'm sorry.
Approximately, okay.
So I'll round to 7. So then I need to have a t-table. Find out here. So 025 column, 7 degrees of freedom, right there, 2.3646. 2.3646. And then what was my other number? Ah, there it is over here. $1.730. So if I try that, finally, this is my plus or minus now, right? I get plus or minus 4.09. That's good enough. So, all said and done, how does it compare to what we did here on the handout page itself? Where is it there? Okay, so we were comparing 1 versus 3, which is the middle case here. So here, with the middle case, we ended up with minus 3 plus or minus 3.58 using the assumption of equal variances, okay? Now, taking that away and not making the assumption of equal variance, we get plus or minus 409. So the confidence interval here turned out to be wider in this case. It's not guaranteed to be wider. It might be wider, it might be smaller. That depends on the details of the numbers again. But anyway, this one ended up wider. And so in this case, we said 0 is in the interval. If we had a plus or minus 409, we would still say 0 is in the interval. So it doesn't change that gross conclusion for the example. So, kind of in a painstaking manner, that's the business of carrying out a confidence interval now based on the Welsh T idea. Any questions on that? Anything more I should say about that? Kind of messy to do by hand. We're lucky that some of our software programs will do this for us. And we just need to know that our software program is doing this for us, because sometimes the output produced by, for example, SAS, doesn't really say what it's doing. It just gives you the final numbers, and you need to know what it's doing. The only way to know what it's doing is to be able to work out at least one case by hand yourself and test the program out to see whether it's agreed with your hand work. Yes.
Does SAS actually compute this test using different variances and with samples of different sizes? Can you do that?
Yeah, it'll do that.
Okay.
In fact, that's what I want to turn to next then, since that's the end of this particular handout. I've got some SAS examples here to look at, and so we can see what SAS is producing for us in some of these kinds of problems. So let's see. If I can do this. So the data is inputted here in the usual way with SAS, multiple entries per line, style. And the first thing I did was a proc print run. So that printed the data here, so we can look at it maybe in expanded form. So the groups are 1, 2, 3. So there's 3 groups, and then the RESP just stands for response. This is artificial data. I don't know what this response is. Okay, so there's some responses, and with 3 groups, we have 4 observations in each group. Then I asked for, well, sorting the data. And then I ask for proc means by group. Run. So the proc means starts to give me these summary statistics. So here for group 1, summary statistics. For group 2, summary statistics. And then continuing on the next side, for group 3, summary statistics. So that was produced by the SAS code here, proc means. Okay. And the last proc is proc GLM, general linear model. Class group model RESP response equals group, and then run. So the last proc is the proc GLM. What did that produce? Well, it produced this. What does it say? It says it right here. The GLM procedure. It produced the rest of this output. So it gives us some information about the class variable and how many levels it had and what its values were, total number of observations used, and then it gives us this analysis of variance table. It's got the standard stuff in it. It's got the model, the error, corrected total is just our total. There's the degrees of freedom, sums of squares, mean squares, F value, and finally, the last entry is the p-value for the F-test. I presume you all know what a p-value of a test is, so there it is, produced by SAS. The p-value being very small, less than our standard value of 0.05, so we should reject H naught. Now, SAS also produces underneath that sort of a shorter version of an ANOVA table with what it calls type 1 sum of squares. And following that with another line for type 3 sums of squares. And there's some purpose to those. Unfortunately, these kind of sums of squares have no effect in a balanced case. this is a balanced set of data. We have the same number of observations in each group. So with balanced data, these lines down here are identical to the model line up above, and so we just ignore them. If we have unbalanced data, then these two at the bottom become something different. And then we have to worry about, well, which one would we use? What do we do with them? And so on and so forth. But that's for a later topic when we get into unbalanced data. So for the moment, just casually notice that the type 1 and the type 3 sums of squares are identical to the original sums of squares up above. Okay? So this is what I call just a basic bare bones SAS run to compute the analysis of variance table and do the F-test. That's all it has on it. Any questions or anything more I should add about that? Looks straightforward enough. All right, let's do another SAS. Which is that here. So here's a new set of data. This is supposed to be somewhat self-explanatory. It says, here's the meaning of 1, 2, 3, 4 for the group numbers. We're planting sugar beets, and the response is the yield of sugar beets from the field. I'm not sure what the units are here for this example. But anyway, 1 is a field with no fertilizer. 2 is a field January plowed. 3, January broadcast, EC, and 4, April broadcast. So what are they doing with the fertilizer in 2, 3, and 4 is indicated there. Plowed under or broadcast just means throw it on top of the soil. So they've got 4 different types of fertilizer applications for growing these sugar beets. There they are described. So we input the data, again, multiple entries per row, on the yield in those 4 cases. And there it is. And the first thing I do is just to print the data so I can look at it. Proc print run. And so here's the data. And we can see the 4 cases of no fertilizer. There's the responses. And then the 2s, the 3s, and the 4s follow seeing the print of the data. Then I sorted the data by group, and then I gave proc means. So this is exactly the same as the previous handout, right? Exactly the same thing. And so we should be seeing similar kind of output. We see the group 1, the summary statistics, the group 2, the summary statistics, the group 3, there they are, group 4, the summary statistics are there. Okay. Then the code said run proc GLM, class is called group, model yield equals group, and here's a new wrinkle. Least LS means, least squares means group / tdiff. So there's a new line there. We'll have to see what the result of that is when we get to it. Okay. But other than that, this is the regular proc GLM with one new addition to it at the end. So let's see what it produced. So here it starts to say at the bottom of the second page, the GLM procedure, boilerplate description there. And then we get the, on the third page, the ANOVA table, degrees of freedom, sums of squares, mean square, F, p-value. Notice how the p-value is very small. It's certainly less than 0.05. We would reject H0 and say somehow the yield is affected by these different fertilizer methods. There's type 1 and type 3 sums of squares here. that are exactly the same as the first sum of squares, and that's going to happen every time the data is balanced. So we learn nothing new there. So finally, we come to the new thing where it says in here, to give us a clue as far as what this means, this is from the least squares means sum command in there. So it gives us the idea that the groups are officially labeled in the data 1, 2, 3, 4. The means are these numbers here, and if we would go back and check, these would agree with the summary statistics that we saw earlier on these 4 groups. And then this is sort of a number that's going to be used by this procedure. So number 1 refers to group 1, number 2 refers to group 2, etc. down the way. On another day, if the groups were defined by some other symbols, not 1, 2, 3, 4, but some other symbols, then the program is going to still set up these numbers 1, 2, 3, 4 over here on the right, and then we would have to make the correspondence back and forth to see what those numbers meant. So finally, we get to this table down below. Now, this is labeled this way, first of all, I/J. So I is the row index, J is the column index. So you notice this 4 by 4 array that appears here. And what we would have in this layout is the top, there are 2 numbers in each position. The top number is the t-test statistic. What's the hypothesis? Well, it's sort of implied. You want to test, one mean equals another mean, or the difference between the 2 means equals 0. So the hypothesis isn't stated here, but it's implied. Well, I'm sorry, I stated that wrong. Here it says in the label, T for this H naught, that the 2 means are equal. And then the second entry is the p-value, as it indicates here. The amount of probability greater than absolute 0. Now, this is a p-value for a 2-tailed test. P-value for a 2-tailed test. And it's a little hard to describe in this shorthand language here of the output. It says probability greater than absolute value of t. Well, strictly speaking, that's not correct. Because if t is negative or positive, absolute value of t is going to be a positive number. And then greater than a positive number would be some area under the t distribution. That's what this says, but that's not what it is. This is just some language, I guess, for expressing this is the p-value for a 2-tailed test. So anyway, for the first t-test, here's the value for the test statistic and the corresponding p-value. It's less than 0.5, so we would reject H naught. Then here's the next one, comparing 1 with 3. And here's the next one, comparing 1 with 4. And looking at those p-values quickly, they're all significant. The other 3, noting these p-values here, are not significant, right? None of the remaining 3 went under 0.5, so they're not significant. So the first row are all significant. So 1 is different from 2, 3, and 4. But then as far as the difference between the others, 2 with 3, 2 with 4, and 3 with 4, this difference is not significant. Remember, this data had a certain context. 1 meant what? No fertilizer? And the other 3 were some amount of fertilizer applied by some means. So that makes some sense in this conclusion that we're making here. One is different from the other three, but there's no difference among the other three. The means were back here again in this tableau. So we can see that the mean yield for one was less by quite a bit from the others. So what this handout then illustrates with this last layout is how to do pairwise t-tests. By the way, these would not be Welch t-tests, right? To say that, but these would just be regular, we would call them pooled t-tests, right? So those are regular pooled t-tests for comparing two groups. And it gives us all of them in that kind of a tableau. Okay. Any other questions or comments about this set? All right. All right. Here. Come to another one. The entire SAS object here for this one then. And let me try to explain the data here a little bit. It's hopefully somewhat clear. But anyway, we're collecting data about a survey which was done on child rearing. So I call it the child rearing data. And the respondents were parents, I guess. And so the parents were described by other surveys, conservative males, conservative females, liberal males, liberal females. So anyway, the parents were given some questionnaires, perhaps trying to ascertain their, I don't know if this is political, liberal, conservative, or just general in life, liberal versus conservative, I don't know. But anyway, you get the idea. Somehow the parents were classified as either being conservative or liberal. And then, so in the data, we have inputting of attitude, group. And so the meaning of the numbers 1, 2, 3, 4 for the groups are as you see in this layout right here. Okay. So we have the attitude about child rearing and then the group. So two numbers are input multiple times per line here. And so we have some operations, a proc print. This prints out the data that you see coming up down at the bottom of this first page, and then continuing on the second page. "22 observations in all. With 22 observations, we can't have equal sample sizes, right? 5 observations per group would mean 20 in all, and 6 observations per group would mean 24 in all. So we don't have equal sample sizes here. Curious. I didn't spot that ahead of time. But anyway, there's a print of the data that we have. What comes up next? Well, after that, this is something new, a proc format. What I want to establish is some kind of verbal formatting. So I want, in this value line, I want 1 to stand for cons male, conservative males, 2 to stand for conservative female, 3 to stand for liberal male, and 4 to stand for liberal female. So I set up that with this proc format here. Then, let's see, I do a bunch of stuff here in the following proc GLM. Class is the group. Model, attitude equals group. Attitude is the response. Then what I do is a means command, group / hope test equals BF. And I put over here in the comment line, this is going to produce Levine's test for you. So this is how I could get SAS to run a Levine's test. Okay. And I think the BF stands for Brown Forsyth. There was Levine who wrote his initial paper which said, subtract off the group means from the data, then take absolute value. Brown and Forsyth in the subsequent paper said, it's better to subtract off group medians before taking absolute value. So this BF stands for the Brown-Forsyth version of Levine's test. Then I gave least squares means group / tdiff. That one you saw in an earlier SAS program, right? That's going to do the pairwise testing on differences. Run t-tests on the differences. Okay. And before the run command, I slid in the format line group L period in that line, and then run. So let's just look at the output from that much first of all. So what do we see coming up here? Here's the data printed on page 2. It says the GLM procedure. Let's see what's here. Well, in the GLM procedure, notice that the values, where am I at here? Right there, are the verbal names for those 4 categories, not the numbers 1, 2, 3, 4. Okay, and that's from my format line in the earlier code. The second thing I noticed about this list here is if you look at the original data, the first one was conservative male, then conservative female. Okay, that's the order in which I set up 1, 2, 3, 4. When I come over here, the first one that appears is conservative female, then conservative male, then liberal female, then liberal male. What the program did here was to shuffle the groups around a little bit, and I think fundamentally what it's doing is to put these names in alphabetical order. You may not want that to happen, but it just did it without us suspecting. Okay. So watch out for a little detail like that. It doesn't matter for this output, but on another day that might affect your output. So then we see the ANOVA table right here. The sums of squares, the mean square, the F for p-value is very small, so we would reject H0 and say somehow the response is different depending on these 4 characteristic groups. Now when I look down here at the type 1 and the type 3 sums of squares, I notice that they're identically the same as what we had up here in the first line. And so I think I misspoke earlier today when I said if you have unbalanced data, these bottom 2 come out different. I think it comes out the same because the data is proportional. Now, what that exactly means, I don't think we have to get into here today. But there's a few other cases where these bottom two sums of squares will agree with the top one. But we're not interested in that, so we can just skip those bottom two sums of squares. Now we come to, on page 4, well, in this handout is page 3, we see the label here for what we asked for. Test for homogeneity of attitude variance. It's going to take absolute deviations from the group medians. Remember, that was our approach for running the means test, right? So it presents us with this analysis of variance table, and there's an F value in it and a P value. And so we would say, since this is less than 0.25, we should reject equal variance. So reject the hypothesis H naught of equal variance. So that's what SAS gives us, and that's matching pretty much what you saw in my earlier handout about running the means test. We would subtract off the medians, take absolute values, and then do a regular analysis of variance here, analysis of variance table test, and that would be a test of equal variances. So here's what SAS gives us, and it's enough to allow us to do the test. I'm not sure where this is coming from, actually. It says GLM procedure. There it is. And there we can see their 4 groups are labeled again in alphabetical order, not original order, so we have to be a little careful about that. The sample sizes here now we can clearly see are not all equal. But we get means and standard deviations. Well, I didn't ask for them with proc means, right? So here they're coming out. If they're of any use for us, they might be in our report. To have those numbers. So then we come to, what did I ask for next in here? It was right in here, still in the proc GLM. There's the means test. So now we're on this least squares means group slash tdiff. And use the format. So that produced the next output. So from least squares means. So it gives us the means and the reference number. Now notice here that in the least square mean output, number 1 refers to conservative females. Now that's different than my original data, right? So here's a place where we have to be careful when we watch this switching around of names. So 1 refers to conservative females, 2 to conservative males, 3 liberal females, 4 liberal males. So that's the meaning of 1, 2, 3, 4. And we look at this table, same as the one we saw in the earlier example. I is here, J is the column index. And so if we kind of just scan these, we have in both cases the test statistic and then this two-sided p-value. So those are the two numbers in the array. If we look at this, we're just going to look at the p-values. Not significant, 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 significant. So the only one that I see that's not significant is that one right there. All the other pairwise comparisons are significant with a t-test. Now that's 1 versus 2. So we trace that up here and we say 1 versus 2 is conservative female, conservative males. So there's no difference between conservative females and conservative males. All other pairwise comparisons are significant differences. Okay. So that table was the same as the kind of table we produced with the other example from the least squares means command. Now what comes up next? Let's see here. Class is group. Now here's something different. Where group in 1, 2. Var means variable we're analyzing is attitude. Format group in L. And so there's something right there that's going to be run. Now what I'm trying to do here is to compare group 1 versus group 2. And that's all I want. I don't want all of those comparisons. I just want that one. So here's some syntax that presumably will do that for me. So let's see what came out when I did this. Okay, so here we were at 1, 2, 3. Bottom of page 3 was that 4x4 table of t-tests. Then finally, turning it over, I get this layout from the t-test procedure. So the way this is labeled, conservative male, conservative female. Now, I'm talking about 1 versus 2, and you remember that here, the program said 1 and 2 were conservative females, conservative males. But 1 was for females and 2 was for males. Now we come here, and we're a little bit confused because 1 is now male and 2 is female. So why did it do that to us? It's another just little reminder that we have to look at this output really carefully, not just believe it on face value, because we might be tricked up by the software. So for the males, conservative, there's a mean, standard deviation, and such summary statistics. Same for the conservative females. And then it's going to take the difference and give the mean, standard deviation, standard error, and then what does it give us? Oh, the next layout, now I see what I'm looking for. The next layout gives us the same means, but it's giving us 95% confidence intervals. And so for the means singly, there and there, but for the difference between the two, there's the interval. And then it gives us 2 confidence intervals on the difference. one based on the pooled t-test, and the second one, as you see with the Satterthwaite name, that's the formula assuming unequal variances, estimated degrees of freedom and all that. So there's some confidence intervals of two types for the difference. So now what do we see next? Same list. This is a 95% confidence interval for standard deviations. And my recommendation for you would be to just throw that away. We haven't talked about what those formulas are here in this class. And I'm not sure which ones they're even using in SAS. I have to go back and look at the basic documentation to figure out what they're doing, because there's numerous possibilities for how they're testing about variances. So I don't know what that is. Let's just leave it go. And then all of this would be the same. Now, so that has the basic output that was called for by the commands. Let's see, where was it? Right there. Okay. Now I'm going to do the same thing as you see comparing 1 versus 3. And then I'm going to do the same thing again, comparing 3 versus 4. So basically, I ran, excuse me, basically I ran 3 pairwise comparisons here with the proc t-test. And the output that you see at the end of this handout from this one and from this one would be similar to what we just talked about for this first case. So you can look at the numbers on your own, and I think that would be just fine. Questions on this handout? Anything more I should say? Yes?
I realized that in the test the homogeneity area between variance, we use alpha to 0.25.
Yes.
So what if I decide to use alpha to be 10%, then I'm not going to reject the 100%. So what is the ideal alpha that we use?
Well, any hypothesis test has to have pre-specify some alpha level. And our rule, let's say for this class anyway, in testing variance equality for the means test, use alpha equal 0.25. You wouldn't get that recommendation from all other statisticians. This is sort of subjective judgment. You use a bigger alpha level on that test. I think Dr. Stolini came up with that recommendation from things that he was reading, because he wanted to use this test about equal variances in a stronger way than I do. Dr. Stolini would say, let's start by first testing equal variances. If I decide that variances are equal, let's go down the road where I use pooled t-tests. If I decide back there on the test that the variances are unequal, then I'm going to use Welch tests. Now the pooled tests are better than the Welch tests. They have higher power and so forth. So what he basically said is I want to be very, very careful about making a type 1 error at that first hypothesis test about equal variances. So one way you can do that is to use a higher level alpha. And he came up with, from things that he was reading, alpha equal 0.25 for that test. Now, I don't use the test of equal variances in a two-stage manner like he does. I don't actually think that's even correct to do that sort of thing. as soon as you have second hypotheses being tested from the same data that you used up here to do your first test, your alphas of 0.5 down here are no longer alphas of 0.5 because they're dependent on things that have happened before in your analysis. So anyway, I don't believe his method is correct. I don't think he says it's correct either. But I think it's just his recommendation for how to do things. Okay, well, I think we're out of time today, so let's stop there. We'll start a new topic then on Thursday.